Hello everyone, welcome to another session. Yes, so today we'll be dealing with nuclear physics, dual nature of radiation and matter, and semiconductor. Okay, so basically, the major equations. So in every class, every session, we'll start with the major equations. So here in nuclear physics, these are the equations which you have to always keep it in mind. R is equal to R naught, that is radius of a nucleus. R is equal to R naught a to the power 1 by 3. Density of a nucleus is mass by volume. Mass, which is equal to mass of one nucleon into A divided by 4 by 3 pi R cube. And nuclear force theory. So nuclear force is a force which holds the nucleons together, as we know that. So this is like for an atomic number less than 20, most stable nuclei have n to the p, that is neutron proton ratio, nearly 1 by 1. So above 20, n by p ratio will be 1.52. Nucleus is unstable here. And for an atomic number greater than 83, there are no stable nuclei. So mass defect is a difference between mass of a constituent nucleons and the nucleus is called the mass defects of a nucleus. Okay. So here is a representation of an atom where X is your particular atom, A is your mass number, Z is your atomic number. So 1 AMU is equal to 1 by 2 mass of carbon minus 12 atom. 1 AMU equal to 931.5 MeV. Okay. So these are the major. So binding energy of a nucleus, that is binding energy of a nucleus is energy released when constituent nucleon are brought from infinity to from the nucleus. So binding energy of a nucleus is energy released when constituent nucleon are brought from infinity to form nucleus. Okay. So this is Einstein's equation, E equal to mc square. Let's go to the numerical problem. So the magnetic moment of a revolving electron around the nucleus varies with principal quantum number as which of the following. So here L is equal to, that is L is another principal quantum number which is equal to NH2 pi and mu is equal to EL2m. So directly you can see the magnetic moment from here. You can see magnetic moment. So mu equal to ENH2m into 2 pi, where mu is directly proportional to n. Okay. So for uranium nucleus, how does its mass vary with volume? So mass of a nucleus is nuclear density into volume. So nuclear density of an atom is constant, that is 10 to the power minus 17 kilogram per meter cube for a nucleus. Therefore, the mass of a nucleus is directly proportional to the m is directly proportional to the volume. So a nucleus at rest splits into two nuclear parts having radii in ratio 1 is to 3. Find the ratio of their velocities. So we have an equation r equal to r0 a to the power 1 by 3. So if you are taking r1 as for the first nucleus, and R2 is the radius of the second nucleus. So R1 is equal to R naught A1 to the power 1 by 3, R2 equal to R naught A to the power 1 by 3. So if you divide this R1 by R2, you will get A1 by A2 equal to 1 by 27. So the ratio of their masses is M1 by M2 equal to 1 by 27. So according to principle of conservation of momentum, the magnitude of P1 is equal to magnitude of P2, that is M1 V1 is equal to M2 V2. So V1 by V2 is equal to M2 by M1, which is equal to 27. That is M1 by M2 is equal to, that is velocity V1 by V2 is equal to M2 by M1, which is equal to 27 is to 1. So your answer will be option D. What is the energy released in a fission of 2 kilogram of uranium-235? Given energy per fission is equal to 2 mega electron volt. So energy per fission, they have given what it is, 200 mega electron volt. For an uranium-235, the number of atoms in 235 G is 6.03 into 10 to the power 23. So number of atoms in 2 kg of uranium 235 is 235 in that is 2 kilogram, 2 into 10 to the power 3 into 235 into 6.023 into 10 to the power 23. So n is equal to 5.125 into 10 to the power 24. So we have an equation. What is it? The energy released in fission of 2 kilogram of uranium C equal to 2 mega electron volt into n into 1.6, that is charge of an electron, 1.6 into 10 to the power minus 19 joule. If you solve this, you will get an answer 1.64 into 10 to the power 20 joule. Okay. Next one is radioactive material decays by simultaneous emission of two particles. Respective half-lives of is 16 and another is 8-10 years. So the time in years after which one fourth of the material remains. So n equal to n naught e to the power minus lambda 1 plus lambda 2 by t into t. So directly you can give the equations, that is e to the power lambda 1 is 1620, lambda 2 is 810. So if you solve this, your time period you will get 1080. Okay. So in basically nuclear physics and dual nature of radiation, so they won't ask any twisted questions. They'll be giving straightforward questions which you're having straight equations. So okay, so that you have to put it in mind, and definitely you have to be thorough with the equations. So in dual nature of radiation and atomic physics, these are the major equations. So one is E equal to h nu, that is energy of a photon is equal to h nu. H is Planck's constant and nu is your frequency. For the application, why this formula is used is to find the energy of a photon. Next one is W naught is equal to h nu 0, which is equal to hc by lambda 0. W naught is the work function, nu naught is the threshold frequency, lambda naught is equal to threshold wavelengths. So relation between work function and that is the application. So K max, kinetic energy, max is equal to half mv square. So as we know that h nu, which is equal to h nu by w0, which is equal to h nu minus nu 0, and k max is equal to half mv square max, which is equal to ev naught, e equal to charge of the electron, lambda equal to h by p, lambda equal to root of 2me, and lambda equal to h by root of 2mev. And we can see that, so these are the direct equation. You can expect the direct numerical problems. Okay, so that they will give all the terminologies, just you have to put the values and solve it. Okay, one such equation: what is the frequency of a photon whose energy is 66.3 electron volt? So they have given E equal to 66.3 electron volt. You have to find the frequency. E equal to h nu, so nu is equal to eh. Okay, directly you can solve it. Answer is option C. Calculate the energy of a photon of wavelength 6600 Armstrong. Okay, so unit Armstrong is nothing but 10 to the power minus 10. So again, it is a direct equation. You have to find the energy of E equal to h nu, but wavelength they have given. So we have a different equation here. E equal to hc by lambda. So energy of a photon is hc lambda. So directly you can put the values. What is the frequency of a photon whose energy is 66.3 electron volt? So that is also direct equation. V equal to h nu. You can solve it. Calculate the energy of a photon. Again, what will be the photon energy of wavelength 5000 Armstrongs if the energy of a photon corresponding to a wavelength of 7000 Armstrong is 4.23 into 10 to the power minus 19 joule? Okay, so your explanation is E2 by E1 is equal to lambda 1 by lambda 2. That is, you will solve as energy 1 is equal to h lambda 1, E equal to h nu 1, that is hc by lambda 1. Then E2 is equal to hc by lambda 2. If you divide E1 by E2, you will get lambda E2 by E1 is equal to lambda 1 by lambda 2. Directly lambda 1 they have given 5000, lambda 2 they have given, E2, E1 they have given, E2 they have given. So you can find out. Next one is semiconductors. So semiconductors, basically all the materials is divided into metal, insulators, and semiconductors. So there will be a energy gap, that is, in every material there will be two energy bands. One is valence band, another one is conduction band, and there will be a gap between this valence band and the conduction band. Okay, so in metals you can see that from valence band the distance between that, or the energy gap will be nearly zero. Nearly zero. Why? Because it can easily conduct, which means it can easily expel one electron from valence band to conduction band easily. So in an insulator, you can see it is greater than 3 electron volt, which means the distance from valence band to conduction band is very high, so that even if you give a threshold energy, you cannot expel an electron from valence band to conduction band to for a conduction, for a conduction of an electron. So, but in semiconductor, the EG, that is energy gap, will be less than 3 electron volt, but they are not pure conductors. So instead to make it to a pure conductor, you have to give a threshold energy so that you can decrease the energy gap and you can expel one electron from valence band to conduction band. Okay, so for one intrinsic, for that there are different kinds of semiconductor, pure semiconductor. One is germanium, silicon, etc. Okay, so for that the number of electrons will be equal to number of hole, which is equal to Ni. Okay, so the total number of the current is given by I equal to current by electron plus current by holes. So for an extrinsic semiconductor, so you will convert this intrinsic semiconductor into extrinsic semiconductor through a process called doping, which means you will add impurities. Okay, so there are two types of semiconductors. One is p-type semiconductor, then another one is n-type semiconductor. In a p-type semiconductor, the number of holes will be very large when compared to number of electrons, and that is a majority carriers is holes in p-type, and n-type your majority carriers will be electrons. Okay, for a PN junction diode, the effective barrier height under forward bias is V naught minus V. Effective barrier height under reverse bias is V naught plus V. So the dynamic resistance RD equal to delta V by delta I. Basic equations. Okay, identify the relationship between the base current amplification alpha and emitter current amplification beta, which is very basic, direct question. So IE is known as IB plus IC. So this is about the transistor. So IE, that is emitter current, is equal to base current plus collector current. So IE by IC equal to IB by IC plus 1. So 1 alpha is equal to 1 by beta plus 1. So alpha is nothing but beta by 1 plus beta. The current gain of a transistor in a common emitter configuration is 50. If the emitter current is 5.5 milliampere, find the base current. Okay, so you have to find the IB. They have given alpha, that is 50, and emitter current IE is equal to 5.5, and we have an equation IE equal to IB plus IC. So you have to find the emitter current, and the alpha they have given us IC by IB. Okay, so just putting in this equation, you will get, or just it is a direct equation, you can solve it. A transistor having alpha, that is current gain, is equal to 0.90, which is used as a common base amplifier. If the load resistance is 5 kilo ohm, RL is 5 kilo ohm, and the dynamic resistance of the emitter junction is 50 ohm, then calculate the voltage gain. So AB is equal to direct equation. Voltage gain is equal to current gain into load resistance by emitter resistance. So alpha they have given 0.90, RL is 5 kilo ohm, which is 5000 ohm, then RE is 50 ohm. So directly you can calculate AB. What will be the power gain of a transistor if its a value is 0.80 and the value voltage gain is 95? So power gain is defined as a ratio of the output, that is output power to the input power, and it can be also determined as the product of the current gain and voltage gain. So alpha they have given, voltage gain is AB 95. The required equation, this is general equation, AP is equal to A, that is output, alpha into input. Okay, the value of a output direct current, if the peak value of output current is given as a 0.095 ampere. So that is also I naught, what they have given 0.095. The required equation is I dc is equal to 2 I naught by pi. Directly you can put. Okay, so this is like, so I'm just winding up the session. So before that, I have to tell you, like, whenever you get a question paper, the first thing is that try to solve all the easy questions first, then go for the moderate question. So there will be all the question papers of IMUCT is set up like, not at all IMUCT, for every entrance exam I'm telling. So there will be easy questions, moderate questions, little bit tricky questions. So if you're very thorough with the theory, you can directly solve the easy question, and if you are very thorough with the equations, you can directly prove the moderate questions. Okay, then go for the tricky question, in which it is a combination of both theory and numerical. So, and all the as I told, all the laws, Lenz's law, Faraday's law, Biot-Savart's law, Coulomb's law, all the laws you Ampere circuit, every laws you have to be thorough, because they will definitely ask question related to every laws. Next one is, the simpler ones, like, this nuclear physics, digital electronics, semiconductor, they can't ask any, twisted questions. They'll be directly asking, straight questions. So just, put all your effort and, study well. So we'll be meeting, hopefully. If you're joining here, we'll meet. Okay, thank you so much.